In this second calorimetry video, we're going to look at heat transfer between two objects. So we're going to look at a couple different scenarios and explain what we can calculate from them. In the first one, we're going to look at two identical aluminum blocks, except one starting at 40 degrees Celsius and one starting at 20 degrees Celsius. If you put those two blocks in contact, they're going to reach thermal equilibrium. Essentially, they're going to reach the same final temperature. And in order to figure out what that would be, we essentially just take an average of the temperatures, since we have the same amount of each material, and we can assume that no heat energy is lost to the surroundings. We would say that the final temperature would be 30 degrees, and we would be right. In another situation where the two aluminum blocks aren't the same size, it gets a little bit more complicated, in that you basically could multiply the mass times the initial temperature, plus the mass of the other block times its initial temperature, and then divide by the total mass, and you would be able to accurately predict what the final temperature would be. Now, in a third situation, where the two objects are not the same, there's going to be another consideration we have to take into account. So when we take a block of silver, say we take a 30-gram block of silver that starts at 100 degrees Celsius, and we add it to 75 grams of water that's starting at 25 degrees Celsius. If we try to take the same approach that we did to the last one, what we would predict is that the final temperature is going to reach 46 degrees Celsius. However, when you put the silver into the water, what you would actually observe is a much smaller temperature change. You would observe, or with respect to the water anyway, and you actually only get a final temperature of 26.6 degrees. So why is that? Well, silver and water are obviously two different materials, okay? And we've been assuming that all materials transfer heat and store heat the same. However, each material does not, okay? So, and the term we use to quantify this is specific heat. And that's the amount of energy it takes to change 1 gram of material 1 degree Celsius. So water has a significantly higher specific heat than the silver, okay? And therefore, it's much easier to change the temperature of silver, which is why it underwent a much greater temperature change than expected. And water, conversely, takes a lot more energy. It's going to absorb a lot more energy from the silver for its temperature to change that much, which is why the temperature only went up by 1.6 degrees. Okay, so here are just some examples of different specific heats. You can see that water is very, very high. Most materials are significantly lower, and metals are the lowest, right? So here's what we can do. We can say that we use Q to represent the heat energy transferred, and we learned about that in the last video. And we can say that the silver loses heat and the water absorbs it. But the amount of heat that the water absorbs is going to be equal to the amount of heat the silver lost. And we know that we can represent the heat transferred as the specific heat times the mass times the change in temperature. So if we expand these two equations, what we'll be able to do is calculate that final temperature. Now, notice that we're representing delta T here as the final temperature minus the initial temperature. All right. So now we plug in the values that we have. So we saw that the specific heat of silver is 0.235 joules per gram degree Celsius. The mass is 30 grams. And then what we can do is solve for the final temperature. Now, we know that the final temperature is going to be the same for both the silver and the water. So we can leave that as the same variable and basically just perform some algebra, isolate that variable, and solve for the final temperature. And when you do that, you do the math out, you distribute, and you get the final temperature to be 26.6 degrees Celsius. So that would be a fairly complicated calculation that you could do involving calorimetry and the transfer of heat between two objects. Now we'll take a look at a slightly simpler calculation problem where we're not solving for the final temperature, but we're simply solving for the mass. So say we take a piece of iron, we don't know its mass, but we know the specific heat of iron, and we know its initial temperature is 500 degrees. If we put it in 240 grams of water at 20 degrees Celsius, we can use this same system where the heat gained by the water is equal to the heat lost by the iron. Okay, and when we expand those two equations, so Q equals mc delta T, or in this case, they switch the m and the c, and you plug in the values, what you will be able to do is solve for the mass of the iron, and we would find that the mass would be 107.3 grams of iron. So those are just a couple examples of calorimetry